G'day, in this video we are going to begin to unpack the kinematic equations. So we'll be covering dot point 1.1.5. We're looking at module 1 and inquiry question 1, still our focus being on describing and predicting straight line motion. But our content statement is all about being able to begin to understand these three equations here. They are known as our kinematic equations. Technically there's an extra two, but these are the only ones that are directly mentioned in our syllabus. You can find the other two using these three, and these are things that we'll begin to unpack in this video and the video following. Essentially, these kinematic equations show the relationships between the measurements of time, distance, displacement, speed, velocity, and acceleration. So our key focus today is to introduce these kinematic equations. Again, three are directly mentioned in the syllabus and your data sheet actually, but there are two more that we'll explore today. We'll begin to unpack how and why each equation might actually be used. There is a contextual reason why you would pick one equation over the other or multiple equations over another when you are solving problems in physics. And then I'll also complete a sample question today to demonstrate that application. So first off, let's have a look at the 5 variables that will be a part of these kinematic equations. These are variables that we're already familiar with, but these kinematic equations will include most of each of these values. So you will see time, displacement. There will be 2 velocity measurements that we see, an initial and a final velocity. So U and V is a notation that I'll be using here in this video. And then acceleration itself will also be included in these kinematic equations as well. So here we have the 5 equations. This is one of our more common and simple ones. V equals U plus AT. We have S equals UT plus half AT squared. S equals U plus V over 2, all multiplied by T. We've got V squared is equal to U squared plus 2AS, as well as S is equal to VT minus half AT squared. So a pattern that you might start to notice is that all 5 of these kinematic equations actually contain 4 of our 5 variables that are included in all of them. So for example, this equation here, V squared equals U squared plus 2AS, is missing the t variable. Similar pattern exists for all the others. Each of the equations is missing a different variable. So what that effectively means is that each equation is able to relate 4 of the 5 variables that are a part of the kinematic equations, and one of them is missing. So when we're looking at how to use the equations, we're looking for scenarios where we know 3 variables and we're trying to find one unknown variable with our formula. So for example, if I knew initial velocity, acceleration, and displacement, I could calculate final velocity as an unknown. Similarly, if I knew another combination of 3 variables, so final velocity, initial velocity, and acceleration, for example, I could rearrange the equation and calculate for S. Could say the same for any of them. As long as you know 3, you're always able to calculate for the one unknown, which makes each of these equations useful because it means that we can make a calculation for one of these measurements when we only know 3 different variables that are associated with, again, the kinematic equations and the kinematic measurements that we know how to take. Something to keep in mind though, as I acknowledged before, the datasheet only includes 3 of these kinematic equations. So you will find it at the beginning of the formula sheet where we're looking at motion, forces, and gravity. Some of these other equations that we see here will be a part of module 1 as well as module 2. Some even come up in the year 12 component of the course, but these 3 are the ones that we're looking at the moment. In the next video, I will be showing you a little bit about how we actually get these equations, how they come to be. So that will, I guess, help to make a little bit more sense of where they come from. But I will also show you how you can find the other 2 equations when you're only given these 3 equations in the data sheet. So we're going to head over to a whiteboard and have a look at this practice question. I'll demonstrate how to use a couple of these kinematic equations in there, and that should set you up for beginning to complete some practice problems in class. So in this question, we're looking at a car. It's accelerating from rest to 22 meters per second east at a rate of 3.5 meters per second. What we're being asked to do is calculate the time taken to reach this velocity. So what we should be doing first is beginning to construct a data column. That is our first step here. That's what I'm going to look at doing to begin with. So I can see first that we've been given a velocity here, it's in meters per second. And based on how the question is worded, because we're getting to 22 meters per second, I know that this value is a v value, it's a final velocity. So I'm going to write that down first. I can also see a rate here of 3.5 meters per second, meaning that this is an acceleration value. Now, I did say before that when we're using our kinematic equations, we want to have three different variables. There aren't any other values that are currently given in this question, or not directly anyway. However, we have been told that we started at rest. And when we do have an object at rest, it is implied that u, the initial velocity, is 0 meters per second. So that is another piece of data that I can extract from the question, even though there was not a number to go with it. The next step that we need to take is selecting an equation. Now, remembering that when we're selecting an equation, we need to make sure that we can use some of the values that we collected in our data column, and our equation also includes our unknown value. In this case, what we've been asked to do is calculate t, the time taken to reach 22 meters per second. So time is unknown. At this point, we've got the right conditions to be able to select a kinematic equation. We have 3 of the known measurements and 1 unknown measurement that we can calculate for. Moving over to our formula sheet, I can see here that I have v, a, and u, but t is unknown. And thankfully, we have an equation ready to go that works with that. We have v, u, and a, and t as an unknown. So we have all the variables that match up. Again, 3 known, 1 unknown, which means that we can begin to calculate for t. So the equation that I'm going to use is v equals u plus at. Our next step is to just do a quick units of measurement check. So because everything is in standard units, meters per second squared, etc., all working with SI, it's going to mean that our t value at the end is going to be calculated in seconds, which is exactly what we want. We haven't been given a specific time to report to, so we should be reporting in seconds because we haven't been told otherwise. So we're trying to find how many seconds, in other words. Next step is to solve, then substitute. So what I'm going to do first is solve for my unknown t, and then substitute my measurements in. That's going to get me my answer at the end. So to solve for t, what I'm going to do first is write at, and I'm going to move u to the other side. So that's going to be v minus u. Then I'm going to do t is equal to v minus u on a. I can then substitute those values in. So that's going to be 22 minus 0 over 3.5. And that's going to come to approximately 6.29 seconds. So what that means is the car was able to get from rest to 22 meters per second east in 6.29 seconds. Now that gets us our answer for part A. So that's our first section here. But we've also been given a second question, which is part B. So for part B, we're being asked to use the data that we've been collecting to then also calculate the displacement of the car during the time when they were speeding up from rest to 22 meters per second. So in this case, we're being asked for a different value that we do not have yet in the question. So I'm going to restart my data column. And I'm actually going to identify first, because this is the big part of the question, S is our unknown value. So this is a new value that we need to calculate for, which means that the equation that we use needs to include it as well. Now, from this position, we have a little bit of flexibility because we already have 4 known values and 1 unknown value, meaning that multiple kinematic equations could be used with the data that we have to be able to calculate for S. Now, I can see here when I'm beginning to select my equation that I already have a kinematic equation which has S as its subject, which means it's probably going to be the most useful equation to me to calculate for S. You could use the other one that's there. It also has S in its equation, but this one is going to reduce our workload a little bit. So with a strategic selection of the first equation on the data sheet, I'm going to be using S is equal to ut plus a half at squared. No solve is going to be required. I can just immediately substitute in. So when I put my numbers in, S is going to be equal to 0, because 0 for u times any time is going to be 0. So then I can put in my half at squared. And when you put this number in your calculator, you should get a number which is approximately 69.1 meters. Now, because this displacement is a vector value, we should also be giving a direction, not just a magnitude. We can see at the beginning of the question, we were told that the acceleration was going from rest to 22 meters per second east, meaning that the displacement of this motion would have been in an easterly direction. And there you go, application of our kinematic equations for two different simple calculations. We'll do more of these in class. Thank you very much, everyone. In the next video, we're going to unpack these kinematic equations a little bit more. I'm going to be spending some time deriving these equations, which means giving some actual concrete reasoning for where these equations come from. And I'll also spend a little bit of time showing you some ways that you can use the formula in the data sheet to come up with the other kinematic equations which don't appear there. But I'll see you in the next video.